Okay, so on to 2.2 part 2. We did part 1 on Monday. All right, so we're going to move into things that are not just single terms with exponents and coefficients. We're doing sine and cosine. Okay, it's a matter of memorization that you're going to have to do this. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, the sign on this one, sine meaning S-I-G-N, okay, the negative, that's really important to not forget, okay, because it's easy to get them mixed up. All right, so we're just going to practice. So dy over dx is equal to 2 times the derivative of sine. The derivative of sine is cosine of x. Okay. All right. They are very kind to rewrite b for us, but that's something we could have realized ourselves, but it's important to see it. So if you see a constant in the denominator, you don't have to be worried about division or anything like that. You can rewrite it as a fraction coefficient on that. All right. So again, it's going to be dy over dx is equal to the derivative 1/2 times the derivative of sine. The derivative of sine is cosine. Okay. Remember, they're never empty. Okay. So the x has to be in there. You can't just write cosine. You can't just write sine. All right. All right. And then this is a combination of what we did last part and this part. And so when I do y prime, hold on, my dog is trying to bite me as I write this. We do y prime. The derivative of x is just, remember the exponent's 1, bring it down, then you change the exponent by subtracting 1 from it, so you're going to get exponent of 0. So the derivative of x is just 1. Okay, and the derivative of cosine is negative sine x. So it's going to change from a plus to a minus. Okay. All right, and then last one is combining by subtraction, and we're just going to do part by part. And so we'll have our dy over dx. That is my favorite way to write it because it reminds me that it's slope. It's change in y over change in x. Instead of delta, they're using d's, but that helps me. So if you notice, I'll do that more than I do the y prime. And the derivative of cosine is just negative sine x. And then I have my negative pi thirds. And my derivative of sine x is just cosine x. So you're just going to be substituting what the derivative is for those things. There's not much of the adding or subtracting from the exponent and multiplying to the coefficient. Okay, so the next thing, we've got our trig functions, basic. We will go into more depth. You'll do tangent and secant and cosecant, but we'll get there when we get there. So this one's real hard. You're going to really struggle memorizing this. I'm being extremely sarcastic because the derivative of e to the x is just e to the x. Okay, it is very simple. So you just have to watch for coefficients or if they add in things. So this one, part A, f prime of x is 3 times the derivative of e to the x, which is just e to the x. I know it seems like a trick. It's not. It does get harder if the exponent's not just x. We just aren't there yet. So these are the very basic rules that you're going to use. That's why the section title is Basic Differentiation. Okay, so we'll get into some of the more complex things eventually. All right, f prime of x is equal to, so the derivative of x squared is bringing the exponent down, subtract 1 from the exponent. I'm not going to write a 1 as the exponent. You can. It's not wrong if you do. And the derivative of e to the x is just e to the x. And from the last theorem, we learned the derivative of sine to be cosine. So derivative of sine x is just cosine x, minus the derivative of e to the x is just e to the x. Okay. All right. Rate of change should be a familiar phrase to you because you do rate of change in junior high. You do rate of change as a freshman when you talk about slope. So rate of change is the same as slope. When you're talking about rate of change of a graph, you are talking about the slope of a graph. Average velocity is a rate of change. Okay. So if you're talking, and that key is average velocity is a rate of change. So average velocity is the same as your slope. So if you're asked for average velocity, it is going to be slope. And so it is change in distance divided by change in time. Okay, so like Distance is usually, distance or position functions are usually given a s of t. So we'll do velocity, average velocity is equal to change in distance, delta s. S is given, and then change in time. Often you might see it as ds over dt. Okay, so that's kind of important there. Be helpful to us as we get there, but that'll be our average. So keep in mind, subtracting your s values or your distance values over subtracting your time values, not any different than subtracting your y values over subtracting your x values that we used in slope before. Okay, so we're going to have a word problem. All right, a billiard ball is dropped from a height of 100 feet. The ball's height, s, at time t, is the position function. Okay, so they gave us our position function. That's our s of t is equal to negative 16 t squared. Okay, and then where s is measured in feet and t is measured in seconds, find the average velocity over the given time. Okay, so these are domains. So those are your input values or your t values. That is not like an ordered pair x comma y. That is an x and an x, in this case a t and a t. So what you're going to do is you're going to plug in 1 and plug in 2, and you're going to subtract their outputs divided by subtract your inputs. So if I am doing part A, I am going to do s of 2 minus s of 1 all over 2 minus 1. That is all I'm doing. Okay, so no derivative at this moment. We're doing average. The derivative would actually give you something called instantaneous, which we will get to eventually. All right, so I'm just going to have negative 16, Mickey, stop it, negative 16, 2 squared plus 100, minus, I'm going to put in parentheses, so I make sure I subtract all negative 16, 1 squared plus 100. All over 1, because 2 minus 1 is 1. All right, and when I simplify that and I plug everything in very carefully and make sure I do that, this is a problem you could do without a calculator. The numbers are not so large that you couldn't, but if you have a calculator, it'll be easier. And you'll get negative 48 feet per second. All right, so then B. We're going to do the same thing. You're going to do S of 1.5 minus S of 1 all over 1.5 minus 1. Okay, so you're going to plug those in. Negative 16, 1.5 squared plus 100 minus negative 16 times 1 squared plus 100. And then all over 1.5 divided by 1 is, or 1.5 minus 1 is 0.5. And then you're going to simplify that, and you'll actually get negative 40 feet per second. Okay. Last one. If you notice the bottom, the distance difference in our time is getting smaller and smaller, which means you're getting more of an exact slope. Okay, instead of a slope across 2 points, your points are almost becoming 1. So you're taking basically a secant. Average slope is more of a secant, and instantaneous is a tangent. And so since you're taking those bottoms together, it's kind of like that example where we had these 2 points. We did their secant, these 2 points, and their secant, and then eventually we get it and we get a tangent. Okay, that's essentially what they're trying to show you here. Last one, you're going to do S of 1.1 minus S of 1. All over 1.1 minus 1. Go ahead and you're going to plug these things in. Okay, and then when I do that, I simplify it and I get negative 33.6 feet per second. So those are your average velocities. Okay, velocity and position. We talked about that a little bit, but velocity is the limit as your change in time approaches 0, kind of like what we were just doing. If you notice, our change in time was getting smaller and smaller, of s of t plus delta t minus s of t. And so that's just a difference in your input values, getting smaller and smaller. So if you think of delta t eventually being 0, that you have s of t minus s of t. So they're exactly the same point. Again, that's what makes it a tangent, kind of like I talked about before. So velocity function is equal to s prime of t, which is your position function. Okay, so this is a little bit of a physics area. So it'd be calculus-based physics. So if some of you, when you go to college, you'll take a calculus-based physics class. And so that's just a really important thing to remember, is that velocity is equal to the first derivative of your position function. When we get into things with acceleration, we will use derivatives to do acceleration as well. All right, so a position of a free-falling object, neglecting air resistance under the influence of gravity, can be represented by this equation. That's important, okay? G being gravity, T is your time, V sub zero, it's also pronounced V naught, N-A-U-G-H-T naught, as in nothing, times T, so velocity, your initial velocity is what that would be. Time has not happened, no time has passed, and your initial position would be S sub zero. Okay, so that's initial velocity and initial position. And then G is gravity. Okay, so, and it says that in the words, but sometimes it helps label it. So depending on how they give you the information, you'll use two different things for gravity. If you're doing it in feet per second, you'll use negative 32. This is for Earth. If they'll ask you to do a different planet or a different situation, they'll give you the parameters for it. And if you're doing meters, it'll be negative 9.8. If any of you have taken a physics class, those might be familiar values to you. Okay. All right. So first example that we'll do. This is a lot like what you would see on your AP test, the free response questions. Okay. All right. So at time 0, so no time has passed, a diver jumps from a platform diving board that is 32 feet above the water. Okay. This says see figure. I didn't put the figure on it. It's not a super complicated figure. So all it is here's my diving board off a platform. This whole thing is 32 feet. That's the information given. And we have a person jumping off. There's my little stick person diving. Okay. And he's going into the water. Okay. I know I'm an amazing artist. All right. So we have that. Because the initial... Nikki, stop it. Because the initial velocity of the diver is 16 feet per second. So we already know that this is our V naught. Mickey, stop it. All right. So we have this initial velocity as